Hey everyone, today we're going to start our lesson on the introduction to limits. So first we're going to examine this function and we're going to determine whether or not it's continuous and how we know that. Now first of all, when we examine the function that's given to us, this is a rational function, meaning a fraction. So when we have rational functions, most rational functions are not continuous. So we need to determine what are those points of discontinuity. So the first thing that we're going to need to know is to factor both the numerator and the denominator. So when we factor the numerator, we would get x minus 3 times x plus 1. In the denominator, when we factor that, it would be x plus 3, x minus 2. So upon inspection, we notice that none of these factors cancel. Okay, remember that when factors cancel, we would have a whole. So right away, I know that there are no wholes. But remember that with fractions, which this is what this is, and rational functions, we would have vertical asymptotes when the denominator is equal to 0. Remember that asymptotes are lines, and therefore we should write them as lines. Our vertical asymptotes here would be at x is equal to negative 3 and x is equal to positive 2. So therefore, we already know that this function is not continuous. Now we know that because we have those vertical asymptotes as we stated here. And we also could determine if we have any horizontal asymptotes. When we have horizontal asymptotes, we have to compare the degree of the numerator with the degree of the denominator. Now, since the degrees are the same, then that means that we would take the coefficients of that highest degree and divide them. 1 divided by 1 is 1. So therefore, we also have horizontal asymptotes at y is equal to 1. So now we're going to go ahead and take a look at the graph. This is the graph of that particular function. And you'll notice that we have those vertical asymptotes as we stated at x is equal to negative 3 and at x is equal to positive 2. Additionally, we can see that the horizontal asymptote is at y is equal to 1. No holes as we determined before. So based on this graph, our analytical analysis of the function is correct. And all the discontinuities that are present are, as we stated before, we have vertical asymptotes at x is equal to negative 3 and 2, and horizontal asymptotes at y is equal to 1. Now we're going to use that same graph to fill in these pre-calculus statements about our graph. And then we're going to write the calculus limit notation. Now a limit is the intended y-value of the graph. This should be familiar from our previous pre-calculus classes and also in Algebra 2 when we discussed end behavior. As x is approaching negative infinity, the graph of f of x is approaching, and we're going to look at the graph here. From negative infinity, that's this side right there, we can see that the graph is starting to level out at y is equal to 1. Now it's very important that the solution, or rather the answer to these statements here, remember that f of x represents the y value. Our y is it's intending to go to 1. So this is going to be our very first limit. The limit as x is approaching negative infinity. Now this is important as well. You need to know what you're finding the limit for. And it's the function f of x. And our solution for that limit is 1. Now we're going to do the same thing, but for the right side of the graph. As x is approaching positive infinity, the graph of f of x is also approaching 1. And that's because the horizontal asymptotes determines both the left and the right side of the graph. So our limit as x is approaching positive infinity of f of x is going to also equal to 1. Now these limits here, these statements, which are limits, for when x is approaching a particular number. Again, we're looking for the intended y value. Where are the y's going? And you'll notice here that these are directional statements. It's telling us from which direction we're going to examine the graph from. So it says, as x is approaching negative infinity from the right, the graph of f of x is approaching what value? So I'm going to look back at my graph. I'm going to look at x is equal to negative 3, which is right here. Notice that that's where we have our vertical asymptote. If we're coming from the right, I believe, yep, the right, that's this side here, we see that the graph is going down forever. So that means that our limit, the answer to our limit is not going to be a particular number as in the previous two, but it's going to be negative infinity because it is going down to infinity. So when we write our limit, it's going to be the limit as x is approaching negative 3 from the right. So we put a little plus sign as if it was almost like an exponent, and that's just to indicate that we're looking at the graph from the right side of that value. Again, of f of x, and we already determined that the answer to this limit is negative infinity. Now we're going to examine that same value, but from the left. So I look back at my graph. Here's x is negative 3, our vertical asymptote, and we see that on the left side the graph is going up forever. Therefore, the answer to this statement, the graph of f of x is approaching infinity. And our limit statement would be written as the limit as x is approaching negative 3 from the left of f of x is going to equal to positive infinity. Now let's look as x is approaching 3 from the right. So now we're looking at when x is approaching positive 3. Positive 3 is right here. It is actually a point on our graph. If that's the case, that means that both the left and the right are approaching the same y value. That coordinate here is 3, 0. And since the graph goes through it, both limits from the left and from the right are equal to 0. Remember, limit is the intended y value, and sometimes it actually does go through that particular point, so it will have a numerical solution. So, as x is approaching 3 from the right, the graph of f of x is approaching 0, and it's the same case as when it's approaching from the left. Therefore, our limit statements would be the limit as x is approaching 3 from the right of f of x is equal to 0, and the limit as x is approaching 3 from the left of f of x also equals to 0. Now we're going to examine a new function, and we're going to use these graphs to answer these limit statements. Our function is 2x squared plus 5x minus 3 over x squared minus 9. Now if we look at these values, right, this is a chart of x values and its corresponding f of x values, or y values. Based on the values in the table, we can look at what the limit would be as x is approaching negative infinity. Notice all of these x values here. X is approaching negative infinity as we read the chart going this way to the left. Notice that these x values are decreasing at an increasing rate. We're constantly going towards negative infinity. Now if I look at these y values, notice that they're consistently getting closer and closer to the number 2. Now that must mean that we have a horizontal asymptote as y is equal to 2, since this is the limit as x is approaching negative infinity. Remember that these limits tell us our end behavior. And end behavior could be dependent on the horizontal asymptote. And once more, if you look at the equation, you'll notice that the numerator and the denominator are the same degree. So we would have to divide those coefficients, and 2 divided by 1 is 2. The same would be as the limit of x is approaching positive infinity. That means that we're going to look towards the right side of the graph, of the chart here. We see that those x values are increasing at an increasing rate going towards positive infinity. And we also notice that those values are slowly decreasing but leveling out at 2. So our limit here as x is approaching infinity of f of x is also 2. For these next two limits, you'll notice that we are approaching the number -3 from the left and from the right. -3 is somewhere right here in the middle because we have -3.001 and 2.999 and -2.999. So if we're coming from the left side, which is obviously the left side of the chart, and going towards -3, you notice that these values here are getting closer and closer to this 1.167. And I'm saying 1.167 because if I'm coming from the right as well, I get the exact same value. That means that at -3, it's not going to change to some other value. It's going to be 1.167 from both sides. Let's examine one more chart, and it's the same function that we're working with. We have these particular x values, and we're going to determine these limits as x is approaching 3 from both the left and the right. So we'll notice here on the chart that we have 2.999 and 3.001. So 3 is right here in between. Now, if I'm approaching x is equal to 3 from the left side and going towards 3, you notice, look at these values. We have -18, -48, -498, -4,000. It's decreasing at a super fast rate. And look at these x values that are just slightly different. Just slightly increasing. So that must mean that we have some kind of vertical asymptote here because we're going towards negative infinity. Now, if we're coming from the right side and we're going towards +3, same thing. If we look at those y values, we go from 8.667 to 52, and then all of a sudden to 502, and then 5,002, with such slight differences in these x values. That means that our graph is increasing super fast in such a small amount of time. So again, we have a vertical asymptote there. And that's why, since it's increasing, it's going towards positive infinity. Now below this chart, you'll see that we have the graph. This is the actual graph of the function that we just found these limits for. And you see we have that vertical asymptote at x is equal to 3, like we guessed. And then we have this horizontal asymptote at y is equal to 2. Now these are all the limits that we found earlier with the charts. But now we're going to confirm those numbers based on the graph. So if I'm looking for the limit as x is approaching negative infinity of our function, if I look at the left side of the graph, we see that it's leveling out at 2. Same thing on the right side of the graph. As we're approaching x is approaching infinity, it's also leveling out at 2 because of that horizontal asymptote. It is important to note that the limit as x is approaching negative infinity or as x is approaching positive infinity, if they're approaching a number, that means that's proof of your horizontal asymptote. Now as x is approaching -3 from the left, -3 is right over here, and you can see that it is slightly above 1. Now at that point, if you're just looking at the graph, you can't exactly estimate what the value is, but because we did that chart, we know that the value is 1.167, both from the left and the right. And if you didn't have the graph, all you would do is plug in that number into your function and you would get that y value. Now, if we're approaching +3 from the left and from the right, we remember that at +3 we have that vertical asymptote. if we're approaching if x is approaching 3 from the left, we see that the graph is going down forever. So we would say that the solution to this limit is negative infinity. And as x is approaching 3 from the right, it's going up forever. So the limit of that function as x is approaching 3 from the right would be positive infinity. So now this is how we would prove that limits exist. This is called the limit existence theorem. Now all this means is that the limit as x is approaching some number, which we're going to call a, from the left must equal the limit as x is approaching a from the right. And it must equal to some number. It has to be a real number. And this is how you would state that you know that a limit exists. If a limit does not exist, then you would say that the limit as x is approaching some number from the left does not equal the limit as x is approaching that same number from the right. So now we're just going to practice with a couple of graphs and finding particular limits and understanding the difference between limits and function values. Remember, the difference is that a limit is the intended y value, where it's trying to go, versus a function value is the actual y value. Where is the function really located at that particular x, and what is its value if it has one? So for this particular graph, I noticed that at x is equal to 2, I actually have a vertical asymptote. The limit as x is approaching 2 from the left of f of x, which is right here, it's going up forever. Therefore, it is positive infinity. And the limit as x is approaching 2 from the right is also going to be positive infinity. Since we can see that on the right side, it is also going up forever. Now the actual function value, since we have a vertical asymptote at x is equal to 2, that means that there is no function value, and we would write undefined. Now for our final question, does the limit as x is approaching 2 of f of x exist? Now, the left and the right do equal to each other, but they equal to infinity, not a real number. So therefore, we would say that it does not exist, and we would write DNE. And we would say the reasoning because the limit as x is approaching 2 of f of x is not a real number. Now it is important to note that a and b, these are called one-sided limits, simply because we are looking at one side of the graph. Versus d, the limit as x is approaching 2, when there's no symbol here, this is a general limit. In order for this limit to exist, both sides must be equal and must equal to a real number. Now let's look at this other example. We're going to evaluate for the limits as x is 2. The limit as x is approaching 2 from the left. Here's the function. Now for the limit, I see that I have this solid circle here, but this is away from my actual function. Remember, the limit is the intended y value of the function. You must follow the function's line, or rather, or curves, whatever the function is. In this particular case, it is a line. Now, if I'm coming from the left, it is approaching, even though it is a hole, it is trying to get to this y value right here, which is 2. The same thing from the right. We are trying to get to that particular y value. Even though it is a hole and it is undefined right there, okay, it is the intended y value. So the solution for that limit would be 2. Now the function value is where it's actually defined when x is equal to 2. On the actual function, we have that hole there on that line, so that is not defined. But at x is equal to 2, we have this solid dot, which is the actual defined value of the function. So f of 2 is negative 2. Now we're looking for the general limit. The general limit only exists if the left and the right equal. Now this is the left and the right, and they both equal to the same number. So yes, the limit does exist, and the limit as x is approaching 2 of f of x is equal to 2. The actual function value, which is negative 2, and even though it's a different number, does not affect the limit. Now let's examine this final example. We're going to look at this graph also at when x is 2. The limit as x is approaching 2 from the left. This is the left side of the graph, and it is going towards a y value here, which is 1. Now the limit as x is approaching 2 from the right, it's going somewhere else. It's going towards negative 1. Now the function value is where we have that solid dot where the function goes through, and that is this point here, which is 1. Now does the general limit exist? We're going to look at the left side and the right side and determine, are they equal? Since they are not equal, the limit does not exist. And you would say because the limit as x is approaching 2 from the left of f of x does not equal the limit as x is approaching 2 from the right of f of x. And this is how you would justify why a limit does not exist, is simply by stating that the left and the right are not equal. So now based on all of those examples, we're going to see if we can answer this question. Does f of a have to be defined in order for the limit as x is approaching a, so that same number for f of x, to exist? So let's look at these two examples to see if it can help us answer that question. If I look here at my function, it seems to be pretty continuous except for here at that hole. This right here, the function value is undefined, but the limit from the left does equal the limit from the right. The function is trying to reach this y value of negative 2. Versus here on this other graph, the limit as x is approaching 1 from the left is 2, and as it's approaching from the right is negative 1. Since they do not equal, this limit does not exist. Now again, to answer the question, does f of a have to be defined in order for the limit to exist? Here, in the second graph, none of those values are defined and the limit does not exist, but that's because the left and the right are not equal. However, in the first graph, that function is also undefined, but the left and the right do equal, so the limit does exist. So, no, f of a does not have to be defined in order for the limit to exist. Now we're going to look at some graphs and practice what we've learned. So here we have this graph of some really complicated function. The limit as x is approaching negative 4. Now here's negative 4. We have this function value, but we're looking for the limit. So I'm going to look for my curve, which is right here. Now you can see that the left and the right are both approaching the same number, which is 3. So that's your limit. The limit as x is approaching 2 from the left. Here is x is equal to 2. From the left, my limit is 1. Now from the right, here's the right side of x is equal to 2. As I'm going to the right, it equals to 3. Now for D, I'm asked about the general limit as x is approaching 2. Now since the left and the right do not equal, you would write D and E, that it does not exist. Now we're going to go to the limit as x is approaching negative 3. Notice that I have a vertical asymptote at x is equal to negative 3. And this is a general limit. So the left side and the right side, even if we can find those limits, the general limit does not exist. It's not a real number, so therefore we cannot state that it exists. Now the limit as x is approaching 3 from the left. Here is positive 3. Now the left and the right would equal, so it actually does not matter where you look, but the left side is going towards, it looks like 2.2. The last two are basically its end behavior. The limit as x is approaching negative infinity. We're looking at the left side and we see that the graph is leveling out at the horizontal asymptote, which is 2. As we're looking at the limit as x is approaching positive infinity, we see that it is going up forever and therefore its limit would be positive infinity. Now we're going to look at one more graph. We have the limit here as x is approaching 2. Here is x is equal to 2, and we see that the left side and the right side are both approaching the same number. Therefore, this limit does exist, even though it is defined here to be something else, but it doesn't matter. We're looking for the intended y value, which is actually 0. For b, we're looking for the limit as x is approaching negative 5. Again, another general limit, so the left and the right have to equal. As we're looking for when x is negative 5, it's right here. Both the left and the right are approaching the same number, which is negative 2. Now we're going to go to the limit as x is approaching negative 4 from the left. Here's negative 4. From the left is right here, and we're going towards y is negative 3. Moving on to D, we're finding the limit as x is approaching negative 4 from the right. From the right, it seems to be going towards a positive 2. Now we're moving on to the limit as x is approaching 4 from the right. So even though there's an asymptote at x is equal to 4, because this is a one-sided limit, we can answer that question. It is going to be some solution. From the right, it seems to be going down forever, so therefore our limit would be negative infinity. Now here we have a general limit for when x is approaching 3. That means that the left side and the right side must be equal. Now on the left side, it is approaching some number, but we notice that on the right side, there's nothing there. Therefore, the left and the right cannot be equal. So that means that this limit does not exist. Moving on to the limit as x is approaching negative infinity. So we're going towards the left side of the graph, and we see that here on the very left, the last part of my function seems to be a point. So this function does not go on forever to the left. This must mean that there is actually no limit because, it's bounded. So therefore, this does not have any value. So this would be does not exist. And for the last one, as the limit as x is approaching positive infinity, we see here that our function is leveling out at this horizontal asymptote, which is 3. And that is our introduction to limits.